Okay, good afternoon. It's the 1st of December, but there are almost 20 degrees outside, so I'm opening my shirt. Last time we have seen through some numerical examples, actually, the computation of some linear algebra subspaces associated to the Jacobian of a manipulator. Could be the geometric or the analytic Jacobian, it doesn't matter. We have seen that there are configurations where something strange happens, namely there is a loss of rank or there is a singularity of the Jacobian matrix if this matrix is square, and we have commented on a specific example using numbers actually that we may lose mobility. So let's recollect these things and try to end this topic with some general consideration and the computation of singularities for some examples of robot manipulators. Very simple, but a computation that can be made symbolically in advance, not configuration by configuration like we did with the MATLAB code last time. I remind you that we developed a Jacobian for a planar 3R robot, and then we fixed the configuration, so the Jacobian would become a matrix of numbers, and then on this matrix we computed in a rather automatic way range spaces, null spaces, bases for those spaces, and then the same also for the Jacobian transpose. Okay? Now we will do something similar, but in a symbolic way, because it's important to know in advance which are the singularities of the kinematic structures. So first of all, we recall some definition. These are configuration. For a given robot, we are in a kinematic singularity if the robot is in a configuration where its Jacobian loses rank, and this definition covers the case of square Jacobian or non-square Jacobian. Okay, so this is more general than just saying determinant equal to 0. Associated to this configuration, there is a loss of instantaneous mobility, so at the velocity level of the robot and effector, or of the task variable velocity that we are considering. So in the classical case, this means that there are some direction in the Cartesian space that cannot be accessed with a non-zero velocity instantaneously. Of course, if we change configuration by giving some motion in the joint space, so some joint velocity, we will change the configuration and then we may escape from a singularity and then recover full mobility of the end effector. We will do this today in a large extent. So for when we have a square Jacobian, so m equal n, for instance, a 2R planar arm when we are considering position x, y of the end effector and then the associated differential quantities, this configuration corresponds to Cartesian poses. So there's a one-to-one mapping between the joint space configuration of the robot arm and Cartesian poses, where the number associated to these Cartesian poses, we have found that the number of inverse kinematic solution is not the generic one. Okay? We will see later on some examples. So keep this in mind. This is a bridge between what we have mentioned when talking about inverse kinematic, about singular cases, and singularity of the Jacobian as a matrix. Okay? The meeting point is exactly this consideration, which is made only for the case of square Jacobian. So when we are in a configuration, so when the robot is exactly in that configuration, suppose that the Jacobian is square, so the Jacobian is singular, its determinant is equal to 0. And then if we ask the robot to have an arbitrary, pay attention to this arbitrary, not for some, any velocity for the end effector in an arbitrary direction, then we are not guaranteed that the solution will exist. Of course, for some specific velocities there may be a solution, for others not. But in any case, we are not allowed to compute this solution by inverting the Jacobian matrix, because this matrix is singular. Okay? However, the point is not just single isolated point in the configuration space. For instance, straight arm or folded arm. The problem is around the singularity. So when we are close enough to a singularity, this strange phenomena occurs. And we will see some numerical example later on. So even if I'm asking the end effector of the robot to execute a small motion with a very moderate velocity, I may need to do this a very large joint velocity. So it's kind of a factor of amplification which is abnormous. And typically, even if the Cartesian velocity requested was very low, let's say 10 centimeter per second or 20 centimeter per second, then the extremely large value of joint velocity asked by the robot will not be feasible for the actuators. So what happens is that we will saturate the actuators, and then we will not even execute that Cartesian trajectory with the desired velocity. So we are losing control in a generalized sense of what the robot is doing. So kinematic singularity are very critical, and not only when the robot is exactly in the singularity, but around those singularities. So this is, I think it's a good reason for investigating the singularity in advance and in a symbolic way, so without relying to numbers, but to expression, because we would like then later to avoid this singularity or to handle them when we have to cross them anyway. And this is a problem that occurs both at the planning level, when we are planning trajectory for realizing some task for the robot, and in real time when we're controlling the actual motion of the robot. Of course, this is even more critical than this, because if you are offline and you're planning a trajectory and you realize that there is some problem, well, okay, before giving this trajectory to the robot, you may reconsider and find another way. But if you encounter a singularity in real time while you're controlling the motion, then something very bad can happen. Okay? So, how do we find this in a symbolic way? Well, when the Jacobian is square, just try to solve this analytical expression. So the Jacobian will be a function of Q, the determinant of a Jacobian will be a scalar function of Q, and we try to find the nonlinear, to solve this nonlinear scalar equation for the Q's that zeros the determinant. Okay? When the Jacobian is not square, and typically it has less rows than columns, remember the columns are associated to the joints, so the columns will weight the individual joint velocity, which are our actual command for moving the robot, while M is the task space, is the dimension of the task space. So having M strictly less than N means that we have more commands than strictly needed to execute some instantaneous task. The reverse situation, M larger than N, it happens, for instance, if you consider the geometric Jacobian of a scalar robot, the geometric Jacobian has always 6 rows because it maps the velocity of the joints of the robot to the linear and angular velocity of the end effector. But the scalar robots have only 4 joints, so only 4 columns in the Jacobian. So the Jacobian is 6 by 4, so M is greater than N. Okay? And in fact, we commented on that. We are not capable of assigning independently all 6 values to the linear and angular velocity with only 4 joints. So the more interesting situation is when we have M strictly less than N or M equal to N. This is the standard case. In this case, we mentioned that we denotes the robot as being redundant with respect to the task. So, but what do we do there? We cannot compute the determinant of a non-square matrix. So we have to remember the definition of rank. So losing rank means that we are not able to find a meaner, an m by m square matrix extracted from the non-square matrix with determinant different from 0. Okay? This means that all minors are singulars. This is one way to check. Or if you want to check only one scalar equation, then losing rank is equivalent to having the determinant of this product, which is a square matrix, of the lower dimension m, because J is m by n, J transpose is n by m, so this is a m by m, small dimension, square matrix, so we can compute the determinant, and the determinant is 0 if and only if the rank of J is less than m. Okay, so this is a way of building one equation to solve for Q in a symbolic way. Of course, this is much more complex, the product of J transpose, than extracting from J a number of minors. So suppose that you have the robot Dexter 8R. We have seen this robot. It was a lightweight robot with cable driven. So 8 joints, and we are considering the geometric Jacobian. So what are the dimensions of this matrix? How many rows and columns? 6 by 8. How many tests like this should I do in order to check that this matrix may lose rank? Ta, ta, ta. So, in how many different ways can I extract 6 columns out of 8 columns? This is the question. First answer gets a prize. Huh? Newton coefficient tells you something? Hmm? These numbers tells you something? 56. The half of what you said. Okay? It's clear? Huh? This is a combinatorial number that you should know very well, I guess. Okay? So this gives you an idea of the complexity of doing, because you have to extract these 28 minors. For each of them, you have to compute the determinant and impose that it is 0 for some configuration. And then verify that where this is 0, also the other are 0. So it's a matter of organizing computation in a smart way, but still it's quite complex. Okay, in fact, this concludes this slide. When we have a large number of joints, we have certainly some difficulty. Well, I could say, well, forget about this. I just make the product of J by J transpose. I have a 6 by 6 matrix. I take the determinant. I let the symbolic toolbox of MATLAB doing this, and you will be lost. So, or better say, the toolbox will be lost because the explosion of the length of this expression is horrible. This is why, if you want to do this, it's better to manipulate a bit the Jacobian. For instance, express it in some special reference frame where it is simpler, because then if you rotate the Jacobian and then you have to do the product Jacobian times Jacobian transpose, then the rotation is gone, while what is remaining is much simpler. I'm just sketching the few slides that we skipped last time, just to invite you to go back and look what they say. Okay, so let's do some simple example of what we have said. Let's start with our good old friend. Direct kinematics is this one. We compute the analytic Jacobian, but in this case it's not relevant what we do, because the first two rows of the geometric Jacobian, those that provides px dot and py dot, are exactly those that are obtained by partial differentiation of the direct kinematic in this case. So this is our Jacobian, okay? So we compute it's a square Jacobian, we compute its determinant. Simplifying things, we find that this is the expression. So L1, L2, and these are different from 0, sine of Q2. So this is just a function of Q2, not of Q1, which means that what matters for singularities in this case is just the internal configuration of this compass. It's not important if I'm here, here, or there. In fact, there's a symmetry with respect to the Q1 variable. Okay? So the singularities are then when sine of Q2 is 0. So either when the arm is stretched, Q2 equals 0, or when the arm is folded, Q2 equal pi. Pay attention, this has nothing to do with the link length. These singularities are there no matter if you have equal length or different link length. Okay? So you remember what happened to the inverse kinematic problem in this situation. How many inverse kinematic solution has this 2R planar robot in the generic case? Two solutions, okay? So my claim is, well, these are singularity of the Jacobian, and this is no doubt. But in fact, they correspond to situation in the Cartesian space. If I'm putting my end effector there and I try to find all inverse kinematic solution, I will find a number which is different from the generic one. So I don't find two solutions, but I may find one solution or infinite solution. Okay? Is it true? Where do I find one solution? Q2 equals 0, so on the outer boundary, or Q2 equal pi when L1 is different from L2. So in both cases, I have only one inverse kinematic solution. Okay? When do I find another number? Infinite. In the Q2 equal pi situation when L1 is equal to L2. Okay, so there's a slight distinction, but what the statement is correct in any case. So in this situation, I have a different number of inverse kinematic solution than the generic one. Okay? Now, this last sentence is very important, but should be taken with some caution. So when I said that I have an inverse kinematic solution associated to this point, and you can see it's my right arm solution. And I would like to go back to this Cartesian point, but reaching the other inverse kinematic solution. Now imagine how can I move from here to there, like moving the end effector, which configuration should I cross? And the claim is that I will certainly cross one of these singularities. Why? Because, for instance, I can stretch the arm and then fold it back in the other configuration. Or I can fold the arm and then come out with the other. Okay, so if you imagine the joint space of this robot, and this requires some fantasy, because you can imagine something like this between minus pi and plus pi for Q1 and minus pi plus pi for Q2. So a square in the plane, but this is only a local representation of the configuration space. Why? Because these points and these points are very close to each other. So when I'm saying pi, or let's say pi minus epsilon, or pi plus epsilon, they are very close, while here apparently they are very distant. In fact, you should take this, let's say, leaf, fold it in one way, and then fold it in the other way, and you will get what is called a donut, or a torus, so the surface representing all the points Q1 and Q2. For instance, you may go around this circle with Q1 and around here with Q2, and then any point, any configuration lives here, okay, on this. Now, the claim is that you can partition this configuration space, which is really a strange object. It's a manifold. This is the mathematical terminology. In two areas associated to this, you have only one of the two inverse kinematic solution. And the boundary divides a region of the configuration space where you have only one solution. Okay? Now, this is almost always the case for industrial robot, for standard robot, but it's not true in general. Pay attention. If you're interested in this, I have a couple of papers that shows that you can change, you can have a robot with multiple inverse kinematic and go from one to the other without passing through a singularity, which it surprised me in the first place, but in fact it's correct. It requires higher order topological consideration, but there exists such robots. The only thing is that they are not common at all. Okay? They have strange alpha values of twist angles and things like that. Okay, another example. Now a three-dimensional case. So the polar RP arm. Direct kinematics, differential kinematics. Essentially, I just need to compute the partial derivative of the direct kinematic with respect to Q to get the analytical Jacobian again. And now it's a square matrix. I compute the determinant, and the determinant is this one after some simplification. Again, pay attention, it does not depend on Q1. Do you think this is a general property or just these two simple cases? So, question again. I have a robot. I have a Jacobian that maps joint velocity to end effector velocity. Suppose that this Jacobian is square. I compute the determinant, and I see that the determinant is never depending on Q1. Is this a general property, or is just the case of the 2R or the polar RRP? General. Why is general? Look at this. If there were, it's general, it's true. If there were Q1 here, then I could maybe find a value for Q1 where this determinant goes to 0. Okay? But Q1, what is Q1? Is the first angle in the Denavit-Artenberg convention. So it's suppose that it's a the first joint is revolute, so it's the angle θ1 between x0 and x1 seen around z1. But remember, x0 is arbitrary. So if this depends on q1, it means that if you change reference frame, you may assign to q1 whatever value you wish. Okay, so the robot may be singular if you choose some reference frame, may be dot if you choose another reference frame, which is, of course, not so interesting if it were the case, exactly because the loss of mobility is only a property internal to the robot and not with respect to some reference frame or to some other reference frame. So even this just qualitative argument can show that you never have a dependence on Q1. Okay? Pay attention. This does not mean that the matrix is independent of Q1. Huh? Pay attention. Okay? Because when you're writing things, you're writing the components of this velocity with respect to frame 0. And so you need to take into account what is Q1, because if you change frame, the norm of the matrix does not change, of the velocity does not change, but you rotate things, and so the components will change. Okay? So the matrix depends on Q1, but the determinant never. Now, we will do same analysis. Pay attention. Here we have a function, a nonlinear function of Q2, and a quadratic function in Q3. Okay? So we have to zero this. And this can be 0 either because cosine of Q2 is 0 or because Q3 is 0. But you see that when Q3 is 0, there's a kind of a double singularity, because if you take the derivative with respect to Q3 of this function, you have still a dependence on Q3, and this will 0 exactly in the same position. So it's a kind of a double 0 when Q3 is equal to 0. Okay? In fact, this is true also when we analyze the singularity. Just this simple analytic result. So C2 is 0, means that Q2 is either pi over 2 or minus pi over 2. It's the same. Just look at this situation. It means that the end effector is placed on the vertical of the joint 1 axis. Okay? Then the rank of this matrix, if you substitute this value, you will discover that not only the determinant is 0, the rank is some more information, because the determinant is 0 if the rank is not full, so it's not equal to 3, but the rank may be 2 or 1 or even 0 in principle. It is never the case. It means that all the elements would be simultaneously 0, and this is never the case for a Jacobian. Okay? So in this case, the rank of J is 2, and this is called a simple singularity, because the decrease of rank is only 1. When you retract the third prismatic joint, so you bring Q3 to 0, then, and you substitute this into the matrix, then you have a rank drop to 1, and this is called a double singularity. Double singularity means that some more difficult case is encountered. In terms of mobility, when you have a simple singularity, so just a drop of 1 of the rank, it means that you lose mobility in one direction in the Cartesian space. When you have a double singularity, you lose mobility in 2 directions. So you're even more constrained in that configuration. Okay? So this is important. Now, let's do the, I don't know if this comes later. Yeah. Let's do the association of the singularities of the Jacobian with situation of the inverse kinematic problem for this robot. You remember, we have solved this analytically. So how many solutions are there in the generic case? Let's say, let's restrict ourselves to Q3 larger or equal to 0. So just booming outside and not retracting. You remember there were 2 inverse kinematic solutions. Otherwise, there are 4. Okay. So when we are with the end effector on the vertical of the joint axis 1, are all joint coordinates defined in an inverse kinematic problem? So suppose that I want to be somewhere there on top of my head with this robot. Do I specify two solutions for Q1, Q2, Q3? Or there's something which is going to infinity, or I only have one solution, or whatever? You remember that? When Q2 is plus or minus pi over 2, or let's say Q2 pi over 2, then Q3 is defined, but I do not specify a value for Q1. So any value of Q1 is okay. So I have infinite solution because Q1 is arbitrary. And in fact, we are in this situation. And the number of inverse kinematic solution jumps from 2 to infinity. Okay? Here, same thing, but even worse. Why? If you remember correctly, Q3 retracted. So when Q3 is retracted, and I'm assigning, in fact, a point which is on the shoulder, this is just a single case, but then the position of Q1 is irrelevant, and also the elevation Q2 is irrelevant because I'm not moving this point. So any value of Q1 and Q2 with Q3 equals 0, assign the end effector at the center of the shoulder. So in that case, the inverse kinematic problem could just find Q3 equals 0, but then could say nothing about Q1 and Q2. So we had a double infinity of a solution to the inverse kinematic problem. You see this association. And this happened. This is nice because it's true that here we don't have any external limit if we don't assume a limit for the prismatic joint. So the workspace goes everywhere. Okay? But in fact, all the singularities occur when the end effector is placed on the vertical axis. If it's out of the shoulder, then the singularity is simple, so degree rank loss equal to 1. If it's retracted out to the shoulder, then it's double. Okay? And then again, if you would flip the third link and go down, you have the same situation. Finally, let's consider this very important case, the case of robots with spherical wrist. So suppose that n is equal to 6, the last three joints are revolute, and their axes intersect at the point, just like in the test. Okay? In the test that you have done, in that case, the first three joints were prismatic. Here is generic. So you have seen that you can always redefine the origins of frame 6 in those cases by bringing the origin at the center of the wrist. You just zero the parameter d6 of Denavit-Artenberg. So you're not considering something outside the wrist center, but you bring this to the center of the wrist. Of course, the position of this frame is dependent only on the first three joint variable. But its orientation, it depends still on all 6 variables, because if you change Q4, Q5, Q6 of the spherical wrist, you will reorient this end effector frame, even if it's placed in the center of the wrist. Okay, so this is the situation. Then we know already that if we give velocity to joint 4, 5, and 6, so to the joints of the spherical wrist, the velocity of the origins of O6, so the velocity of the center of wrist, will be 0, always. So we can imagine that the Jacobian has a partitioned structure, for instance, the geometric Jacobian, with a structural 0 here. These are 6 columns, and these are organized in blocks 3 by 3. The upper part are linear velocities of O6, and the lower part are angular velocity of frame 6, which has an origin in the center of the wrist. So in general, you will have some dependence here. So both moving Q1, Q2, and Q3 dot, and Q4, Q5, Q6 dot will give an angular velocity to the frame, but only when moving the first three joints. you will have a linear velocity to the origin 0,6 or to the center of the wrist. So there is a structural 0. Now in this 6 by 6 matrix with block triangular structure, then the determinant will be 0 if and only if either this and or this matrix, 3 by 3 matrix, have determinant 0. So you have a partitioning of the potential singularity. This is also called decoupling property, because when you are in a configuration such that the determinant of this block is 0, you call this arm singularities. And in fact, they depend only on Q2 and Q3. Here I just let, this is the determinant of J1 as a function of Q1, Q3, but then the determinant will be only a function of Q2, Q3. We have just mentioned this, okay? But in any case, these are related only to configuration variable that belongs to the first 3 joints, so to the main arm, not to the wrist. And these are called arm singularity of this robot. When the determinant of J22 is equal to 0, and this typically depends only on Q4 and Q5, not on Q6, then these are the so-called wrist singularities. And of course, you may be in a combined singularity where the first 3 variable or give you singularity of this block, and the last variable will give you singularity of this block. So you have rank loss which is larger than or equal than 2. Okay? But you have this decoupling. Moreover, this block has an explicit expression which is given by this. Why is that? Remember that the last 3 joints are revolute. So for the angular contribution, the subcolumns which are associated to revolute joints for the angular part contain simply the unit vector of the joint axis. For joint I, you have zi minus 1. So for joint 4, 5, and 6, you have z3, z4, and z5. The unit vector along the 3 joint axes. So you can also give a nice interpretation to the singularity of the wrist. What does it mean that this matrix 3 by 3 becomes singular, so its determinant is equal to 0? It means that the 3 vectors are not linearly independent, which means that the 3 axes of the 3 joints somehow align. So for instance, all 3 lie on a plane, and then you have a rank loss of 1, or all 3 are aligned along the same direction, and then you have a loss of 2 in the rank of this matrix. Okay? So this is quite nice, and in fact it happens, all depends on the second joint angle. So depending on if this is a sequence of the ZYZ or ZXZ Euler type, then you will have a singularity when Q5 is equal to 0 or Q5 is equal to plus or minus pi over 2. Okay. The other thing is, look at this Jacobian. When you have to invert this Jacobian, it's in general 6 by 6. If you want to have an analytic expression of the inverse with a 6 by 6 matrix, you're dead. Okay. But since this has a block triangular structure, you may have an analytic expression of the inverse because you just need to invert blocks which are 3 by 3. Then it starts making sense. Or you do this numerically, and then it's almost irrelevant if you have to invert 1 6 by 6 matrix or 2 3 by 3 matrix. But remember that the inverse of a block matrix like this, so J to the minus 1 has the same structure, and here you have the inverse, and here you have something which you may compute by just the identity. But then you find the inverse in the block, the diagonal block of the element. Okay? So, this question we have already given an answer. So let's move on to trying to invert this mapping. This is the next module. It's divided in 2 blocks. We will make just the first block, or almost all the first block here. So what is the inversion of the differential kinematic? We already introduced this when we mentioned the fact that we would like to realize some velocity at the end effector level with some joint velocity. This is exactly solving the inversion problem, but now at the differential level. And as we mentioned, since this operation is done configuration by configuration, when we are solving for joint velocities, then this is a linear problem, because we take the Jacobian, we evaluate it in the current configuration, and we try to solve a set of linear equations. So essentially, we do the following. This is the differential map. Now I'm using the variable v. It's not important if it's a r dot, if it's v omega, whatever. No? It's some task or Cartesian velocity, and this is some Jacobian, analytic or geometric, multiplying q dot. So if now v is given, a desired v, I want to realize this, and for realizing this in the current configuration, I need to choose q dot, I need to solve a system of linear equation. And if j is square and non-singular, the solution is unique. And it's computed in this way, q dot equal inverse of this. I put here a dependence on q, but in fact, first I evaluate the Jacobian at the current q, so I have a matrix of number, then I invert this matrix, and then I multiply the results by v. Okay, so don't be disguised by the fact that I have a q here, because this operation is repeated for any q, but in practice I evaluate the Jacobian at the current q, then invert the Jacobian, and then move on with the obtained q dot. So this topic, I had 20 slides, but I'm done. There's nothing else to be said on this. I invert the Jacobian. This is true, but there are a lot of things to take care, and 2 of them are this. First of all, what happens when I'm in a singularity or near a singularity? The result is that I will have in this inversion, and this can be intuitively explained. So suppose that this inverse is 1 over the determinant, and then you have the adjoint matrix. Now this is the expression of the inverse. So you have 1 over the determinant. If the determinant is getting close to 0, you have a multiplication of whatever is on the right-hand side by a very, the inverse of a very small number, so you generate q dot, which is very large. This is intuition, and in fact is what happened in practice. So high q dot, how can I discourage such results? Especially because if I can invert the matrix, and I can invert the matrix anywhere except exactly in the singularities, but still when I'm very close, I can invert the matrix, but I have this result, large q dot. So how can I prevent this, even if I have only one solution? Because this is the unique solution, as long as the inverse exists. The second point is, what if J is non-square? And then, of course, if it's non-square and it's losing rank, then I have also the singularity issue. But even if I have a full rank J, I cannot invert it, because it's not square. So what do I do? Okay? So what we will see next is some example of the behavior of such systems, and then some proposal of a more robust inversion. And when I say more robust, I mean that something that can handle redundancy and or closeness to singularities. Before doing this, let me this is a new slide that I added this year because I realized that there was some hole in this presentation. So what I'm saying here is that this joint velocity level inversion, so I'm inverting velocities, can actually be used as a method for inverting successively kinematics, direct kinematic problems. So at the position level. Why? So suppose that you have this direct kinematics. You give Q and you compute R. Okay. Now, if we move to the differential level, we have done this in velocity, but we can do this also with increments or infinitesimal increments. In fact, if I divide it by dt left and right, this is R dot, dr over dt, and this is Jacobian times dq over dt, which is q dot. So the same thing that applies to velocities applies also to infinitesimal motions. Okay? So having this in mind, suppose that you have a sequence of inverse kinematic problems. So I need to find a solution in Q for this point, and I have multiple solutions. Okay, but I can take one. Let's say this with elbow down. The next problem is close to the previous one. So it's not the same, not this R, but it's R plus delta R, with delta very small, so infinitesimal. And I have to solve again the problem. So for doing this, when the next problem is inverting the same task but close to the previous one, then you can follow two possible implementation. One is, okay, this R plus delta R is a new R. I don't care if it's close to the previous one. I have a closed form solution. So I have function that solves the problem. So I apply this. I find the new Q, which is the inverse kinematic solution for the new position. This is what we would do if we don't know that there was a closed solution before. Now, how do we use the Jacobian in this context? Well, you revert the passages. You take the increment, dr, and you invert this by inverting the Jacobian. Just like velocity, you do this on differential motion in the Cartesian space. And you find a variation, dq, of your q. And then you add this variation to the previous solution. You had found already a solution to the inverse kinematic problem before. Now you're adding this increment. And then you are in a new configuration, and you're done. Supposedly, provided that the variation is small, this works. And it's nice to appreciate also the fact that you may not have an inverse kinematic function in closed form, but you always have a Jacobian, and you always can invert the Jacobian. Okay? So this is a handy way. And just to relate things that we've been saying over different lectures, this slides is an example of what I mentioned when we were using numerical method for solving the inverse kinematics. And I mentioned at the end, those methods are offline methods, but in fact could be used also online while the robot is moving. And here is the situation. Doing this is in fact applying Newton methods for solving the next inverse kinematic problem in a numerical way. We have seen it now from a different perspective, just thinking about differential inversion of the kinematic map, so using Jacobians at the velocity level. Okay, but it's exactly the same thing. Okay, now, this is an old slide that I took from an old book, which was representing this problem of inverting the velocity mapping close to singularities. Okay, so here we see our 2R planar robot. You see the boundary of the workspace. Suppose that the two links are equal and unitary. And now you assign a motion from this point, x0, y0, along a straight line to the point xn, yn, which is the end of this Cartesian trajectory. Now, this Cartesian trajectory is made by a line. It's a linear path that you have to realize with, let's say, constant speed, v. So 1 meter per second. You go there. However, you can see that we start relatively close to the boundary, but not so much. And this path comes close to the origin of the Cartesian space. And we know that the origin is a Cartesian space associated to a singularity. In fact, in this case, we would have an infinite number of solutions if we were exactly passing through the origin, because any value of Q1 would work. But if we are generating motion by inverting this mapping, and pay attention, every time you do this, so you do Q dot j to the minus 1 of Q V, and then you have Q plus Q dot times dt, and you have the new configuration, and then you put this new configuration here, you take the new value of V, and you repeat this. So you can imagine this discretizing time with some sampling of 1 millisecond or 1/10 of a millisecond, whatever. Okay? So when I'm generating the joint motion, so by choosing a sequence of velocity in the joint space from this formula, and when I'm getting closer to the singularity, I have a problem of inversion of the Jacobian. Okay? So in this case, if we look at this evolution, these are sample configuration for θ1 and for θ2. Okay? And you see that we are moving at constant speed. Now you have a kind of a stroboscopic view of the 1, 2, 3, 4, 5, 6, and so on, of the configuration of the robot arm. And when you're getting closer, there are Cartesian points which are very close one from the other. So very small increment. And they are associated to a large reconfiguration of the arm, which, let's say, at configuration 3 has the elbow up, and then 4 and 5 and 6 rapidly does a rotation of joint 1. In fact, you can see here the corresponding point. You have a large variation with respect to this. For small increments, large variation of θ1 associated to this singularity. Okay, so in fact, if you divide it by time, you have a peak of velocity, in this case of joint 1, because you're getting close. How close? Well, I cannot tell from this picture, to the singularity. Okay, so this is shown this result. So my idea was, okay, I take this example and I work out numerically. I have a code in MATLAB where I can repeat this task. So I have a 2R robot, planar, starting from here to there. This is the path. And then resolving the differential kinematic, the inverse differential kinematics, and then plotting the stroboscopic view and then all the quantities that I need. Okay? And then I can play around. For instance, this straight line is at 170 degrees from the x0 axis. Okay? So I show the motion, and then I bring this toward 180, progressively getting closer and closer to the singularity to see what happens. Okay? So this is the task that follows in the following slide. These are unit length, because here I can see this dimension is 2, so this is the robot arm when it's straight reaches 2 meters of radius, and I'm assigning a constant speed of 0.6 meter per second for a total time of 6 seconds. So I'm traveling in the Cartesian space for 3.6 meters. So I'm going from here toward close to the end. 4 meters would be the full diameter of the range of the workspace. Okay? So, and this is the first result. With this situation, I'm starting with this configuration. So I'm choosing one of the two inverse kinematic solutions. It doesn't matter which one I'm choosing. And then I'm inverting Q dot and I'm changing configuration. In the new configuration, I'm assigning the same velocity for the end effector. It's always pointing in the same direction. It has the same intensity. And I'm folding the arm. And then here you see this rapid configuration when I'm getting close to the origin. And then the arm folds out again till reaching the final situation. You can see that any configuration in this simulation is the same inverse kinematic solution. So if you start with elbow up, well, here you fold, but it's the same solution. Now it's elbow down just because you reverse the thing. So if you think that this is the left arm, so you're starting like this, or maybe I should do this. You're starting like this, and then you're ending like this. So it's always the left arm. You didn't switch inverse solution. Because for switching inverse solution, you should have passed through a singularity, and here you didn't pass through a singularity. Okay, now these plots are exactly describe the motion that you, this stroboscopic view of the motion. These are the evolution of Q1 and Q2 for that previous motion. These are the evolution in red always of the first variable, in blue of the second variable, of the joint velocities, Q1 dot and Q2 dot. And this is some measure that evaluate the distance from singularity. It's not the determinant, but it's the minimum singular value of the Jacobian, which is a better indication of how close you are to the singularity. But you see, it starts from close to singularity, 0.1, then it grows to 0.7, then at the midpoint of the trajectory, it dangerously falls down, and you're again close to singularity, then recovers, and so on. And since this is a simulation, so we have some numerical integration error. So this shows the integration error in executing the task. So the error on the Cartesian position is 10 to the minus 10, so practically 0, okay? But it's just accumulation of numerical integration error. Okay, so what happens if we live dangerously? We bring this line closer to the singularity. So 178 is the angle. With 180 would be just going across the singularity. And you can see here again, this is a stroboscopic view at selected, so at uniform sampled times. So you see that it folds, and then all of a sudden from here it folds back in order to continue along this straight line, which is almost horizontal. So here nothing seems too bad, except that I notice a large variation of joint 1. But if I look now at the plots, I see here Q2 is, well, rather regular. In 6 seconds goes from minus 50 degrees, then up to minus 150, and then coming back. But I start seeing a variation of Q1. And in fact, if I look at the velocity of this variation, so divided by the time, I see a peak of almost 600 degrees per second. For very short time, I have this large peak. If I look at the distance to the singularity, I'm starting as before with 0.3 around, and now I'm getting even lower, below 0.1. So at 0, I would have singularity. So I'm very close to the singularity. Okay? And in fact, numerical Cartesian error is still small, but a little bit higher than before, because when I'm getting close to a singularity, also the numerical integration process is affected by this. But this is the main, the dramatic aspect. So this 600 or so degrees per second may not be realizable by the actuator at joint 1. So this simulation says, okay, if you had infinite amount of power in your actuator, you would do this. But are you able to do this? So in order to check if this is correct, I'm inserting in the simulation a saturation of the two joint velocity at some level, let's say 300 degrees per second. Reasonable or not, I don't care. I'm not saying how, what is the weight of this arm, so it's just kinematics, okay? And I'm repeating exactly the same motion, and I see almost nothing changes at this level. So it's moving as before, but if I look in detail, I will see that, okay, again, a large variation of Q1 close to the center point of the workspace where the singularity here, but the peak of 600 degrees per second is now cut out by the saturation. In fact, the maximum value is 300 degrees per second, so I'm saturating. But saturating the velocity means that I'm not applying the velocity needed to stay on the trajectory. And in fact, I see that as soon as I have a saturation, there's an error jump. Okay? So the error jump to 6 centimeters and stays there forever. Because once I've lost, let's say, matching to the desired trajectory, I will never recover because there's no feedback control here. Okay? So same situation as before, close to the singular case, but I see that the actual motion, so if I'm predicting what a real robot would do, it would generate an error because of saturation. Okay? So this means that something else should be done if I don't want to live with this error. And I need to go through this. And this is a handy solution, a first solution possible, which goes through doing some kind of damped least square. Instead of inverting my Jacobian matrix, I'm doing damped inversion. This is the terminology that is used. In fact, I reformulate the problem differently. Instead of saying I need to so problem 1 was find q dot such that jq dot is equal to v. Okay? And in case this is square, I say, well, okay, the unique solution is this one. And it's square and non-singular. Now I'm asking something more relaxed. I'm saying problem 2, well, it's find q dot, because this is what I need, and then I don't want really to solve this, so to bring to 0 this, but I want to minimize some term which relates, and let's put also a 1/2, a factor 1/2, just for for ease of derivation, differentiation. So I want to minimize the norm of this. What is this? If I'm finding a q dot which solves this, this would be 0. Otherwise, this would minimize in norm the error on the desired Cartesian velocity. So I'm finding a q dot which does not satisfy the requested task, but it's close enough. Okay? And I combine this with another term. I think it's the same writing. Okay. So with a weighted lambda, a positive number, I'm trying to minimize not only this, because for minimizing this, in particular for solving exactly this, I would have 0 error, but I may have a very large q dot. So I'm putting into the objective function also another term which penalizes large joint velocities. Okay? So I'm trying to find a trade-off between realizing the velocity task at the Cartesian level and having small joint velocities, so that the solution probably would compensate for this peak of velocity, because these are very costly in my objective function. If I'm minimizing this function, I should have the best of both worlds. Now, the nice thing is that the solution can be found in closed form. And there are also alternative way of writing things which are exactly equal if J is square, singular or not, pay attention. No? But if J is associated to a redundant case, so there are less rows than columns, then this expression is more convenient. I leave you as an exercise to show that this expression is identical to this expression, notwithstanding the fact that we have exchanged blocks. The second exercise is, how do you find this solution? Any of the two, they are equivalent. You just take this function as a function of q dot. This is a quadratic function of q dot. So you take the gradient of this function, you put the gradient equal to 0, and you solve. And when you solve, you have this. Okay? Now, here again you find an inverse. Let's look at this. This expression is called damped least square of the Jacobian. Damped because it's a least square, you're minimizing the task error in a square sense, and damped because you want to damp out the joint velocities. Okay? This is a general problem that you find in many other branches of engineering. So here it's nice because you have a physical intuition of what you're doing in the robotic case. Okay. Now, the matrix that you need to invert is this one, J transpose plus lambda, a positive scalar, times the identity matrix. Now, be assured that this inversion is always feasible. So even if J is square and singular, or non-square and losing rank, in all the cases, J transpose is a symmetric positive semi-definite matrix. This is a symmetric positive definite matrix. The sum of these two matrices is always positive definite, and therefore is always invertible. No matter how small is lambda, you can always invert this matrix. Okay? This is a very powerful result if you think about it. Okay? Of course, there's a price to pay. What is the price? That you will have likely a smaller joint velocity than just by inverting the Jacobian, but you may accept or tolerate, or you need to tolerate also some Cartesian error, because this is the trade-off. And of course, if you're sure that you're far of singularities, and this is the reason why you need to analyze the structure in advance, if you're sure that you're far away from singularities, you can solve this problem and just put lambda equal to 0. Because if you put lambda equal to 0, you have this solution still working, and if you look at the situation, this applies both for square and non-square Jacobian. And if the Jacobian is square, you simplify things and you find that this is exactly j to the minus 1. Okay? So let me write it for you once. So if j is square and non-singular, then set lambda equal to 0, and q dot damped least square, this solution, will be j transpose to the minus 1 times v. Okay? But now each of these matrices is non-singular and square, so I can bring the inversion inside and distribute it. So this will be j transpose times j to the minus transpose times j to the minus 1, 1. and then you have this simplification, and you recover what you expect. Okay? So this is very handy. So when you're far off, you put lambda to 0, and you find the exact solution, which will minimize this error norm and, in fact, bring it to 0. When you're getting closer to a singularity, you start increasing lambda from 0 to some maximum level. Because the more you add lambda, the more you penalize joint velocity, so you prefer not to move the robot, but then you sacrifice this in terms of accuracy. So lambda should not be too large. In fact, here I brought you some computation, because once you choose a lambda and you solve q dot, in order to understand what will be the error that you execute for choosing q like this and trying to realize a v, and this error has this expression. Again, I leave it to you as an exercise to find. There's some simplification need. And you can see here that the larger the lambda, the larger the error. Okay? So you don't want to use a large lambda unless this is needed. So very, very, very close to a singularity. And finally, the same technique can be used both for recovering from singularity of a square Jacobian, or if you have a non-square Jacobian to invert, including the case where this non-square Jacobian loses rank, so it's singular according to the definition that we have given. So let's compare the damped least square with the traditional j to the minus 1. And now so we started with 170 degrees, then we moved to 178. Now we're getting even closer to the singularity, 179.5, almost going through. In fact, it's almost, you see that at this level of resolution, I just apparently am going across the origin, okay? And when I do this motion with the damped least square, look what happens. Here, I already see some error there, which is then recovered thanks to a feedback action, okay? So I'm sacrificing this. So let's compare first the stroboscopic view, just the view of how the robot would move. Here is the j to the minus 1, and in fact, I'm starting with this solution, then I'm folding the arm, and all of a sudden, more and more, when I get closer to the singularity, I have this jump of the theta 1 variable, and then I reopen, okay? It's exactly the same behavior as before. Look what happens with the other solution. It's a completely different behavior. Not far away from the singularity, but when I'm here, the robot folds and then gets out in this other configuration, okay? Exactly symmetric to the previous one. And around this position, I'm tolerating some error. I have no error here, but I will have very large joint velocity. So if I consider that those velocities are not realizable, then I will have error even here, as we have seen in the previous simulation. So here you see joint motion with the j to the minus 1 and joint motion with the damped least square. Here you see a jump from 50 degrees to 300 degrees in almost instantaneously. Here it's a smooth motion all over the places. And if I look at the velocities, unsaturated one, here I have a peak of 2,000 and more degrees per second. So clearly, if I can only realize 300 degrees per second, then I will have certainly an error at the Cartesian level. Here it's jerky, but still the maximum values is 80 degrees per second. 80 as opposed to 2,000. So you see that what is the huge differences. But of course, there will be some error. And here, the without saturation, you will still have a small error, only numerical. Here you will have an error which is about 25 millimeters with a robot which has 1 meter and 1 meter length. So on 4 meter workspace, you will have 25 millimeters error when you're getting very close to the origin. And then this error is brought back to 0 thanks to the fact that you're adding to the desired velocity a feedback action. We will come back on this at the end of the course when we are talking about kinematic control, so closing a feedback loop on the error. Okay, and here you see also how it behaves in terms of distance from the singularity. So this in red, or better say, the one in blue, which is covered by this red block, goes up and then goes very close to 0. Okay, and this is the minimum singular value of JJ transpose. When I'm doing pseudo-inversion, when I'm doing damped least square, what I'm inverting is this matrix. So I'm looking at the minimum singular value of this matrix. And it's the same as before, because here lambda is 0. When it gets very close to 0, I'm adding the damping part. So I'm escaping from becoming 0, and then I continue. This is a pictorial view in order to see how should I change lambda. And here I see the damping factor lambda is 0, and then when I'm getting close enough to the singularity, I'm increasing it to 0.1 as a maximum value. And then when I'm getting away from the singularity, I bring this again back to 0. Okay, so this is the whole way in which this method works. Now there is another possible robust method for doing things, not the damped least square. Again, this method works both for non-square Jacobians and for square Jacobians which are singular. And it's similar to the previous case, but we are trying now to expressly minimize the joint velocity vector in norm, but enforcing the solution of the task. So we would like to find a q dot which imposes jq dot equal v, or jq dot minus v equals 0, and minimize the norm. So this problem has, again, a unique solution, which is denoted by this diesis or dash, whatever you want to call it, DIAG, or which is j pseudo-inverse times v, exactly the same. So if you have a square non-singular Jacobian, then this problem has only one solution. And in fact, the pseudo-inverse becomes identical to the inverse. Otherwise, it's some other mathematical object. Now, what is the property of this method? Pay attention. This is the most critical part. The rest is just definition. So we have two cases. If we have full rank, no matter if j is square or non-square, but we have full rank, then we don't lose mobility. Don't lose mobility of the end effector. This means that whatever v we choose to realize, so whatever Cartesian velocity we would like to realize, this belongs to the range space of j. Okay? So it can be realized. And so this solution realizes this, either in the unique possible way if j is square and non-singular, or minimizing the norm of the velocity if we have multiple solutions for a non-square Jacobian of full rank. So if we have a redundant arm, like my body while moving the hand, I can move the hand in several ways, but still moving it in the same way at the Cartesian level, but moving my body differently. Well, this solution tends to move as little as possible my configuration for achieving the same Cartesian velocity. Okay, so it makes sense. So what happens if we have a loss of rank? So either the Jacobian is square but singular, or is non-square but again singular, so the rank is not full. Then there are two cases. Either V belongs to the range of J, so it's feasible, then you cannot invert the Jacobian, but you can pseudo-invert the Jacobian, and you will realize exactly this velocity. Or it does not belong to the range, then this solution, the same solution, automatically minimize the error JQ dot minus V in norm. So it's the closest possible choice to the desired V, just because V does not belong to the range of J. So we use this notation to say that I'm getting one particular solution in the closest to the range space of J. This perpendicular notation means that. Okay, so this is the orthogonal projection of V on Rj. Of course, if V belongs to Rj, then the orthogonal projection is the vector itself. Otherwise, this is what you solve. Now, this pseudo-inverse, how do you compute this pseudo-inverse? Well, the easy way is to use the instruction of MATLAB, which is called PIMB. So you have a matrix, whatever dimension. For instance, this is the J with, let's say, 3 columns and 6 rows. Then you call PIMV J, and you obtain a matrix which is 6 by 3 and guarantees the properties that I will show it now. Okay? But one would like to know what is this matrix. So it can be said formally that given any matrix, I call it J because I'm thinking of the Jacobian, but this applies to whatever context. So given any J matrix, no matter if square, no matter if full rank or not, then there exists always one matrix, unique, J plus, that satisfies these 4 properties. Okay, and this is the pseudo-inverse. Okay, and these 4 properties are easy to remember because the first 2 says that if you do the product and you have a dominancy of J or J plus, then the dominant matrix remains. So if you have J, J plus J, there are 2 J and only 1 J plus, so what remains is J. If you have J plus, J, J plus, the dominant is J plus and J plus remains. And the second 2 identities just says that the product J, J plus and J plus J are symmetric. So their transpose is equal to the same matrix. This is it. There always exists such matrix. Now, there are cases where you can give an explicit expression to this matrix. For instance, if you have a square J and it has full rank, so the determinant of J is different from 0, then the unique pseudo-inverse is exactly the inverse. So this is a natural generalization. In fact, J to the minus 1 satisfies all 4, when it exists, it satisfies all 4 definition of the pseudo-inverse. Another interesting case is when you have a Jacobian like this one, so with less rows than columns, but you have full row rank, which is the maximum that you can achieve. No? The 3 rows are all independent, so this means that you can extract also 3 columns which are independent, possibly in more ways. Then the pseudo-inverse takes this expression, J transpose, J, J transpose to the minus 1, which, by the way, is exactly the expression of the damped least square when you put lambda equal to 0. Okay? So you see that there is some connection. Again, why this? Why it has this? I don't care. I just take this. I verify that it satisfies the 4 defining identities. And then, since the pseudo-inverse is unique, I say this is the pseudo-inverse. Okay? As simple as that. Otherwise, more in general, you need to, the PIMV instruction of MATLAB actually internally calls the singular value decomposition of the matrix, does some elaboration, and then provides numerically the output which satisfies all this. For instance, if you have a 2R arm with L1, L2 equal 1, and you're putting your robot into a singularity, so Q2 equals 0, so the rank is 1, and this is the Jacobian in a generic Q1, and you can see that the first column is twice the second column, so it's clearly rank 1, so determinant equals 0, and this is the pseudo-inverse of that. Now I've written it analytically as a function of Q1, not numerically. Again, how did I find this? It's too long to explain, but just check that this J plus satisfies the 4 relation if J is given by this, so independently of the choice of Q1. And we close with this comment. So suppose that you generate this, and this is the minimum norm joint velocity that realizes the orthogonal projection of V in the range of J. Now we understand why we have computed the range and the null space and so on of the Jacobian last time, because now we have to determine if a desired velocity vector is in the range of J or not. For instance, when the arm is straight, and then we know that it's in singularity, which means that it lost mobility for the end effector. There are directions that I cannot actuate. There are no velocity that I can realize at the end effector level in some direction. The only velocity that I can realize are in the range of J. And the range of J is this direction. So I can only realize a velocity that goes here or there. I cannot realize neither a velocity that goes out, but this is obvious because I'm at the boundary of the workspace, so I cannot go out of the workspace. But what is not obvious is that I cannot even realize a velocity like this. Why? Because this does not lie completely in the range of J. It has a component which is orthogonal to that. So in fact, what I'm realizing is just its projection, orthogonal projection in the range space, and this component cannot be achieved at all. Okay? If I'm trying to use the J to the minus 1 here, I will get just not a number and trash in my solution, okay, because I'm really in a singularity. When I'm using the pseudo-inverse, I will get some velocity, well, realize at least this, if not the whole V. So this is quite an advantageous solution. So the combination of pseudo-inversion and or damped least square are the robust method that are used in practice in the experiment and slowly also in the industry as a systematic way of handling these singularities. And I think, okay, last slide. Last slide, we leave it the next time. Okay. Bye-bye. See you on Friday.